Okay, let's go ahead and begin this video. Now, at the tail end of last class, we said that there are very many reactants that can participate in redox chemistry. Lots of different chemicals can either be oxidized and reduced. And we wanted to come up with a strategy for figuring out which chemicals tend to want to be oxidized the most, which ones want to be reduced the most. And we said that we're going to be able to do this if we choose a common reference point that's known as our standard hydrogen electrode, SHE. And by convention, the reduction of H plus to H2 gas is assigned a reduction potential of 0 volts. We talked about how to build one of these hydrogen electrodes if we really wanted to do that, what it would be constructed from. But the key idea here is that this is our common reference point for making measurements in electrochemistry, and it's assigned a 0 volt potential, a reduction potential of 0 volts, okay? We then decided that the cool thing about this is we could construct one of these SHE electrodes, install it as the cathode in an electrochemical cell that's plugged to this positive end of the voltmeter here, okay? It's our cathode. That's where the reduction occurs. Remember, by convention, red cat, reduction occurs at the cathode. That's our hydrogen electrode. And then the other side of our cell, I would draw a line down through the middle here, okay? It's obviously kind of an imaginary thing to separate these half cells. But if I do so, when I separate the half cells, this other side on the left is our test cell component. We could put whatever we want there. It's half cell. Here it's zinc anode, okay? But we could have some other reactant, and I can measure the potential or the voltage reference to the SHE. Now for this particular half cell operating under this particular conditions, we get a positive 0.76 voltage, okay? If I change the conditions, if I change the ingredients in that half cell, that voltage will change. However, if I operate under my standard conditions for both sides, standard conditions for my hydrogen and standard conditions for my test cell, 1 molar concentration, 1 bar or atmosphere partial pressure of gases, 298 Kelvin. If I operate under standard conditions, I then can say something about standard condition tendencies to be oxidized or reduced. And the way that we decided to do that is a really simple equation that's presented right above this figure, okay? We decided that what we would do is we'd say that the indicated potential or voltage, that's the one that's on the voltmeter, can be decided as being equal to two numbers subtracted from one another. Each of these numbers are nothing more than the half cell potentials. The potentials are the voltages of each individual half cell, if we were to think about it that way. Now we can only find the difference, we can only measure this difference. But if we make the cathode or the hydrogen electrode 0 by default, remember that was the 0 volts. We can plug a 0 in for that one, and because we can measure what the voltmeter actually reads for any test cell we want to, and plug that in, here that's positive 0.76, I can figure out my key crucial information from my test cell. That's this X right here. That X has to do with the reduction potential for my test cell, whatever I put down here. So because I can make the measurement, and because I signed 0 to the SHE, I'm in business. Now in this particular case, I solved for the X, right? I said that last time, it's negative 0.76. Should be a negative. I forgot my negative sign. But to make the math work, that has to be a negative 0.76 volts. And that voltage has something to do with this test cell. It's called specifically the standard reduction potential for that half cell. And I'm assuming, because I'm using the word standard there, that this half cell is operating under standard conditions, which means my zinc 2 plus concentration has to be 1 molar. We have to be right at 298 Kelvin. But if I'm operating that cell under those standard conditions, that number is a standard reduction potential. Now the beauty of that, we're going to get into today. Because what that number tells us is the tendency of a particular reduction half reaction to occur relative to the reduction of H plus to hydrogen. It tells us about the tendency for zinc 2 plus to want to be reduced to elemental zinc, zinc 0 or zinc solid, in relation to hydrogen. Now the cool thing about this is any reduction half reaction with a stronger tendency towards reduction, compared to hydrogen, will have a positive value for their E0 reduction. That's the standard reduction potential that we solved for in the experiment. However, a half reaction that has a tendency towards oxidation compared to hydrogen will have a negative value. And that's what we have here, right? Because we have a negative value for our reduction potential for the zinc. So chemically, what that tells me right away is that hydrogen, H plus, hydrogen ion, tends to want to be reduced more than zinc because of that negative sign, all right? And this is kind of the power of this. Now, we can do this experiment again, not only for zinc, but we can do this for a lot of different substances. And we can make this huge table called the table of standard reduction potentials versus the hydrogen electrode. Now, this word reduction is really important here, because if you study this table very closely, all of the reactions which are listed over here on the left, all of them are written as reductions. They're not oxidations. They're all written as reductions by convention. Okay? Like you can see here, we have iron 3 plus 3 electrons going to the solid. We have zinc 2 plus going to zinc solid. That's the one we just talked about, isn't it? Notice there's a negative 0.76 down here. That was that number that we decided was the voltage that the voltmeter read. Okay, so no surprise, we see the negative 0.76. But there are also reactions up at the top of this table. All right, let's look at this one. Oh, look, it's gold 3 plus 3 electrons to form gold solid. That has a standard reduction potential of positive 1.5 volts versus the hydrogen electrode, okay? So all this is a table of different reactions. All of them are written as reductions. Don't lose sight of that, okay? Only reductions on this table. Only reductions on this table. They're all written as reductions. And what this table then does for us, if you look over on the far right, you'll see basically a list of standard reduction potentials in volt units from very high positive numbers all the way down through 0. That's our SHE, isn't it? And then down below 0, we have what? Negative values. Increasing in magnitude all the way down to negative over 3 volts for the lithium plus an electron to get lithium solid, okay? So very strong positive values to very low negative values, okay? They're in order from high to low, with hydrogen being right here in the middle. This is our reduction of hydrogen, our SHE reaction, okay? So this is our table of standard reduction potentials. Now chemically, what does this tell us, okay? Let's talk about that really fast. Well, it's a list in order from top to bottom of things that really want to be reduced compared and then increasing tendency to oxidize. Okay, so what I'm saying then, let's look up here at the top. What's the top reaction? It's F2 gas plus a couple of electrons to make 2 copies of F minus. That has a standard reduction potential of positive 2.87. All right, so what that tells me, since that's the first entry in this table, is that F2 gas, which is fluorine gas, boy, that stuff really, really, really wants to be reduced. Such a high reduction potential up here at the top. Very, very high reduction potential. Almost 3 volts, which is extremely high. The things at the top of this table really want to be reduced. Consequently, they are very good oxidizing agents. F2 gas is the strongest oxidizing agent on this table because it wants to be reduced the most. The bigger the number of E0, the bigger the standard reduction potential, the more that substance wants to be reduced. Let's look at some other things up on this table. High. Look, we got the gold 3 plus that I mentioned earlier, right? Gold 3 plus reduction to gold solid right here. That's a reduction reaction. Look, its standard reduction potential is positive 1.5. If you can read it on the table right there. That's still a pretty strong or high magnitude reduction potential. It's a positive number. And that tells us that gold really likes to be reduced as well to elemental gold. It doesn't really oxidize easily. Oxidized form is this stuff over here, but the reduced form is the elemental solid. Well, that's no surprise to us, right? We know that gold is one of our inert metals, don't we? It tends to like to exist in the elemental form. That's why it's a precious metal. Silver. Silver's in through here. Another one of our semi-precious metals. Likes to exist in the solid form. And note that it's got a positive 0.8 volts standard reduction potential. So again, all these things up here tend to be pretty strong oxidizing agents because they like to be reduced. So I guess I'll summarize that. Like being reduced. They like to exist in their reduced form in nature, in our natural world. And that's usually how we find them. Compare and contrast that now to the things down at the bottom of this slide, okay? Things way down at the bottom have negative reduction potentials. Let's take a look what's down there. Well, we got sodium plus 1, adding an electron to make sodium metal. Got potassium plus 1, adding an electron to make potassium metal. Lithium doing the same. Calcium, barium. When you see these elements, usually in chemistry class, like sodium, potassium, lithium, what form do you usually find them in? Don't you usually find them in the forms that I'm leaving highlighted, like Na+, K+, Li+? They're usually in their ionic compounds, aren't they? Can we make sense of that? Well, notice that these elements have very, very negative reduction potentials. So what does that tell us about their tendency of sodium plus 1 to want to be reduced and form, say, sodium solid? Or likewise, what does it tell us about the tendency of potassium wanting to reduce and form potassium solid? It tells us that these chemicals really do not prefer that, do they? Because they're really low on our table. The stuff down here at the bottom likes to be or exists in its oxidized form. Likes to exist in the oxidized form way down here. So that's how we usually find these materials in nature, okay? So the cool thing about this table, there's a lot of cool things about this table of reduction potential, but one of them is it lists all these substances in order of how badly they like to exist in their reduced form, from top to bottom. Things at the top are going to be super strong oxidizing agents because they like to be reduced. Down here at the bottom, these are weak oxidizing agents because they like to exist in their oxidized form. Instead, they are really strong reducing agents, aren't they? So it's a list of redox activity from high to low. And that's one thing that's really cool about this, okay? But another thing that's really cool about this, actually there's several things that we'll talk about here, okay? But another thing that's really useful about this table and cool about it is that they give us actual numbers, don't they? For standard reduction potentials for all these different substances. And what that's going to mean for us is that we can use these numbers in this table to calculate what's known as E0 cell, or a standard cell potential for any electrochemical cell operating under standard conditions that we want to set up. So basically what I'm saying is we can set up one of these electrochemical cells like the one on this slide. And I don't have to use the SHE and zinc anymore. I can use whatever anode and whatever cathode I want. And guess what? I can come up with actually a pretty simple equation that if I'm operating under standard conditions, I can predict what that voltmeter will read for any cell I want to. all right? And that's kind of going to be where we're going to head next, okay? So let's try to figure out how in the world that we can do that. We're going to use a pretty simple equation to help us do this. The equation to compute what that voltmeter would read for any cell is given in this highlighted box. It's really, really, really simple. One of the easiest equations we're going to use all semester. What it tells us is that E cell, E0 cell, so we're operating under standard conditions here, okay? Standard condition cell potential, that's what the voltmeter would read, this number right here, can be found by subtracting two numbers. We take the standard reduction potential from that table for the reduction half reaction, and we subtract the standard reduction potential for the oxidation. Reduction minus oxidation, or the cathode minus the anode half cell. All you do is you take the difference between the numbers on that table that we just talked about. And that's how you compute the standard cell potential. Now this is under standard conditions. That's important to realize. Got to be operating at 298. We have to have 1 molar concentration of all the ions, have to have 1 atmosphere partial pressure of gases. But if we meet that condition, we use this very simple equation to quickly and efficiently compute what our voltmeter would read just using the numbers on the table. And it's really as easy as that, okay? Now, how do we know if an electrochemical cell or a redox reaction is spontaneous as it is written? And what I mean spontaneous as written, because you could reverse the reaction, right? So if you react A and B to make C and D, will A oxidize B to form the products, or does it have to work the other way, right? The other way around. So as written just basically means, how the reaction is showing a chemical change. Is that spontaneous? So to answer that question, all you need to do is calculate E cell. If E cell is a positive number, what that means is the reaction is spontaneous. If E0 cell is positive, the reaction is spontaneous as written, and that's called a galvanic cell. However, if E cell is negative, it is not spontaneous as written, and in fact the reverse reaction would be spontaneous. So that's how you tell. Spontaneity of a reaction for electrochemistry, if you can compute E0 cell, you can tell if it's spontaneous or not, all right? Now, important point, sometimes people are confused by this. I think it has to do with the equilibrium constants and so on and so forth that we did earlier this semester. Remember when we had to square the concentration terms and K expressions? Well, you don't do anything like that here. You just employ this very simple equation. Do not multiply the values in the table by stoichiometric coefficients and reactions. You do not need to do that at all. And the reason why is because the voltage is a driving force for a reaction to occur, isn't it? It's a driving force. That has nothing to do with the number of copies involved, but rather that driving force has to do with the innate tendency of the materials under study to want to be oxidized or reduced. It has to do with that innate tendency of wanting to get rid of or add electrons. It does not matter how many copies of a particular substance is involved in the reaction. So never ever multiply by any integers when you're computing these equations. You basically just need to use them here as they're written in the middle of the slide. And honestly, this could not be much easier, could it? All right, so we have now developed a framework to compute our E0 cell for any electrochemical cell that we want to. It's E0 cathode minus E0 anode. You include the signs from the table. If they're negative, that comes along for the ride when you use this equation, but never, ever, ever multiply by any numbers, those values from the table. So it's extremely simple stuff. We can compute what the voltmeter would read for any electrochemical cell operating under standard conditions because we have been organized and came up with that table of standard reduction potential. So let's try a sample problem, because computing standard cell voltages is an important learning objective for this chapter, and I'm 100% sure you're going to see this in a homework. You're probably going to see it on the exam. You're going to need to know how to do this. So what we are to do in this sample problem is to use the tabulated standard electrode potentials to calculate the standard cell potential for the following reaction occurring in an electrochemical cell at 25 degrees. That's the standard temperature. The equation is already balanced for us, we're told, okay? Now again, when you're doing these problems, key in on the words standard electrode potentials. Standard cell potentials. That's very important, that word standard, because that tells us 1 molar concentration, 25 degrees. You can only use that equation on that previous slide for standard conditions. If we're at non-standard conditions, you have to use a different equation. We're going to get to that. But right now, we're only working standard electrode potentials, and I want to stress that. So let's look what we got here. We got aluminum solid being converted to aluminum 3+. Is that oxidation or reduction? Well, we're increasing the oxidation number from 0 to 3+. Clearly, that is oxidation, isn't it? So identify quickly my oxidation half reaction. The aluminum is converted into 3+. That's my oxidation. That's my anode half reaction, or anodic half reaction. What about my reduction, or my cathodic half reaction? Well, what's left? It looks like we take some NO3, the nitrate ion, under acidic conditions, and we convert that to our NO and some water. That's our other half reaction, isn't it? And that's our reduction. Now, how do we know it's reduction? We want to justify that, right? Well, let's take a look at the oxidation numbers. Remember, each oxygen is usually -2, and that's the normal rule for oxygen. That whole nitrate ion is -1. So what does my nitrogen here have to be to make the math work? I think it's +5 from the way I see it. You have 3 copies of oxygens, each at -2. That's -6. And you got to offset that with a +5 to make the ion charge equal to -1. But on the right side, we have our oxygen, which is, again, probably -2. But here it's a neutral compound, so it looks like maybe our nitrogen is +2 oxidation number. So clearly we go from +5 to -2. This is our reduction. All right, so we justified that it is in fact a reduction. We make sense of it. It's a reduction of the nitrate ion into NO gas. So that's our reduction, or our cathodic half reaction. So now we've identified which reaction is oxidation, which reaction is reduction. That's always kind of be your first step here. You got to really do that. Break it into the half cell components. That's something that's important, okay? Now, after you do that, the next step is to use that table. Now, I gave you the table of standard reduction potentials in that colorful printout there the first day of class. It might be useful for your homework now. It takes up like half the page, so it was kind of a big investment of space on that card, so I hope it's useful for you. But we're going to need to use that table now to look up our standard reduction potentials. Those values are called standard reduction potentials. They're all written as reductions. They all are for standard conditions of concentration, pressure, and temperature. So they're standard reduction potentials. That's what their name are. We're going to look them up on the table for both of these reactions. So the first one is the reduction of aluminum. Let's see if we can find that on the table if I go back. Now you have to be really careful when you use this table, okay? The reason why is because you want to find the very, very, very specific reactions under study. And I note that way down here at the bottom, I found an entry for aluminum. Now it's aluminum 3+ aqueous plus 3 electrons making aluminum solid. Is that the one that we want in this problem? 3+ to go to aluminum solid? Yeah, it does involve 3+ and aluminum solid. Now this is written as what? An oxidation. In the table, it's a reduction because they're always reductions, but that's the right reaction, okay? So let's look back and see what the value is for that oxidation half reaction. So I go way back. It looks like it's negative 1.66 volts. So E0 equals negative 1.66 volts versus the SHE, because all those numbers again are versus the SHE, hydrogen electrode. And it's negative. That comes along for the ride, and I wrote that, okay? Now what about for the second reaction? I'm going to need to know my standard reduction potential for this reduction of nitrate under acidic conditions to make NO gas and some water. Now this reaction involves a few more very specific reagents, right? It's acidic conditions, it's nitrate. We got to make this NO gas. So when we go and we look in the table for the entry for that, we want to be very precise in finding the exact reaction of interest, okay? So let's go back to the table and see if we can find that one. I'm going to zoom in just a little bit. Oh, look, I think I found it. right there. Looks like we got the nitrate under acidic conditions making NO, and the value over here on the right that's associated with that is a positive 0.96 volts versus the SHE. So I'm going to go back here, and I'm going to write a positive 0.96 volts versus the SHE. And those are our two standard reduction potentials for both of our half reactions. Now, after we look up the values in our table, we have to solve for what the voltmeter would read, and that's this E0 cell, or our standard cell potential. Standard cell voltage, standard cell potential. This is what that voltmeter would read if I actually set this experiment up with these two half reactions in the two cells under standard conditions, 1 molar concentration, 298. If there are any gases, I don't think there are here, but oh yeah, there are, okay, right here. So 1 atmosphere partial pressure, okay? So what would the standard cell potential be? Well, it's really, really easy from here. We just employ that equation on that previous slide. E0 cathode minus E0 anode. You got to remember the order. The reduction comes first, the oxidation comes second. So we take what? Our reduction half reaction, which is this one, and its value, which was the 0.96. We plug that in for E0 cathode. Easy as that. We then take the other value for the oxidation half reaction. We plug that in with the sign for the anodic half reaction, or the oxidation. We do the one minus the other, that will flip the sign, we'll end up adding them, and we get an E0 cell of 2.62 volts. Note that it is a positive 2.62 volts. So that tells me that this reaction is spontaneous. As it's written, it will occur vigorously, as it turns out, because that's a fairly decent size E0 cell. It's spontaneous as written, and the reason why is because that sign was positive. If that's a positive number, the reaction's spontaneous as written, and this would form a galvanic cell. It would be a galvanic cell. We could set this up, make a battery at 2.6 volts if we wanted to, okay? So it's as easy as that. You just subtract two numbers. Now notice, did I do any multiplication of these values that I got from the table if the stoichiometric coefficients are different in the balanced chemical equation? No, I didn't. I just grabbed the numbers from the table, I put them in the equation, and I solved, and I was done. And that's it. That's how you get the right answer, okay? So there's no multiplication necessary. It's really, really easy if you're at standard cell conditions. Super simple at standard cell conditions, okay? You just use the numbers from the table, and that's all you need to do, all right? So what else can we get from this table of standard reduction potentials? What else can we understand about chemistry, okay? Well, I've kind of been alluding to this, I guess. Maybe I haven't said it in such specific words, but a redox reaction will be spontaneous when there's a stronger tendency for the oxidizing agent to be reduced and the reducing agent to be oxidized. Basically, some things want to give up electrons and become positive ions, like sodium, elemental sodium, for instance, loves to give up electrons, becomes Na+1. Other things like to accept those electrons and to be reduced, and that's just their natural native tendencies, okay? It's not a big surprise. I mean, we've been studying chemistry all year, and we kind of have a feel for how that works. So higher on the table of standard reduction potentials means a stronger tendency for that stuff, that reactant, to be reduced. And the lower you get is a stronger tendency for that stuff to be oxidized. And I kind of alluded to that when we introduced this table here a few minutes back, okay? Now, the interesting thing about that, ultimately, is the placement on the table allows us to sort of predict the spontaneity of redox reactions. Like if you mix two chemicals, we can use that table and the fact that it's in order from things that really want to be reduced to things that don't to predict whether or not a spontaneous reaction will take place, okay? So let's think about that for a second. And to help me with this, what I'd like to do is consider these two reactions down the bottom. One's in the purple, the other one's in the red. Let's look at these reactions. One's spontaneous, one's not going to be, okay? And this is not going to be a huge surprise once we look at it. So this first one takes zinc 2 plus, solid, and it reacts this with copper 2 plus, aqueous. And we basically have a redox reaction in which the zinc is oxidized and the copper is reduced, isn't it? Now, if I was going to compute E0 cell for that, what would I do? Well, I do my E0 reduction, or cathodic reaction, minus my E0 for my oxidation. And as this reaction is written, which is my reduction? Oh, look. It looks like it's my copper, isn't it? Copper is being reduced. Copper has a standard reduction potential of a positive 0.34 volts versus the SHE. And I'm going to subtract the value for zinc, which is my anodic reaction. I got to be careful though when I do my subtraction. I didn't leave myself enough room there, because the zinc has a reduction potential of negative 0.76 volts versus the SHE. So a negative essentially make a positive, and I get a positive 1.1 volts for that E0 cell. For this reaction, 1.1 volts. Now, what would I have gotten if I had done this for the reverse reaction, or the other way around? In other words, we're switching up what's oxidized and what's reduced, okay? Let's think about that real fast. So let's focus in on this purple reaction now, which I have labeled as non-spontaneous. But let's explain why. Well, in this reaction, copper is being oxidized, and zinc is being reduced, isn't it? So if I compute E0 cell for the purple reaction, what do I get? All right, well, I still do cathode minus anode, cathodic reaction minus the oxidation. Well, which one's my reduction here? Well, it looks like it's the zinc, isn't it? At a negative 0.76 volts. And I'm still going to subtract the oxidative reaction, which is the copper, at a positive 0.34. So if I do that, I get a negative 1.1 volts versus the SHE. That's for that second reaction, isn't it? That negative sign should pop out in your head immediately. If you have a negative E0 cell, that reaction is non-spontaneous. All right, so we can use this concept of predicting or calculating E0 and the table to really tell whether a reaction is spontaneous or not. This is a really easy way to do it. You can actually tell based on the placement of the materials in that table as well. But if you get confused by that, you can always fall back on this quantitative mathematical approach. Now, let me show you how to tell, based on the placement in the table, whether a reaction will be spontaneous or not. And a really good way to do that, an example, is talked about on this slide, okay? Predicting whether or not a metal will dissolve in an acid. So it's a very specific type of reaction. But nonetheless, this concept can be extended to more or less any pair redox substances that are listed on your table. So certain metals will dissolve in acids, and other metals will not. So we can kind of make sense of that through this redox chemistry, as it turns out. And to do that, let's kind of key in on this reaction right here. Now, this is one of the reactions that is actually successful. So if you take some zinc solid and you throw it into an acid solution where you get a lot of H+, right? It turns out that what will happen is the zinc will dissolve. Now, dissolve, okay, what do we mean by that chemically, right? Well, the zinc becomes oxidized. Essentially, we corrode the zinc, because again, remember, corrosion is oxidation. But we oxidize the zinc metal to make zinc 2 plus aqueous. This is an aqueous ion which would float around in the solution. We dissolve up the zinc metal because we convert it, we oxidize it into zinc 2 plus. We also get some hydrogen gas in that process. Is this a redox reaction? I've already told you that there's oxidation involved, so hopefully you're answering yes. But let's really kind of break down the nuts and bolts of what's happening here. If we look at the reaction in more detail, the zinc is oxidized. What happens to the H+? The H+ is reduced, isn't it? Let's take a look at the location and the position of zinc and H plus on our table of standard reduction potentials. So I'm going to page back here. H plus, well, that's our SHE reaction. That's its reduction, 0 volts. The other reactant here was zinc. Zinc is way down here at negative 0.763 volts versus the SHE. Zinc is below hydrogen on this table, isn't it? So what does that tell us about the relative tendencies for these two materials to wish to exist in their reduced states? Remember, the higher we go on the table, things that are up here, large positive numbers, they really want to be reduced, don't they? And things down at the bottom prefer to be oxidized, or they want to exist in their oxidized form. That's their tendency. So we have a situation where we're mixing zinc solid with H plus in a reaction system here. And we know that zinc just has a natural tendency to want to be oxidized more than hydrogen. And likewise, hydrogen prefers to be reduced more than zinc. It's vice versa, right? So we know that the zinc will dissolve in an acid solution because H plus, a strong acid solution, because H plus that we're going to encounter in that strong acid solution, it wants to be reduced more than zinc. So these two get together and say, oh, no problem. Zinc says, hey, I prefer to be oxidized. The H plus prefers to be reduced. Mix them together. That's what happens. The zinc gives up the electrons. The H plus grabs them for themselves, and everybody's happy. It all works out, right? Kind of a chemistry match made in heaven. Now, not all acids, or not all metals, can be dissolved in acids. Some metals won't dissolve in a strong acid like HCl. Can we make sense of which metals won't be? Well, let's go back to our table. Well, we saw zinc was below our SHE reaction, and zinc reacted. What about metals above the SHE reaction? Let's see if we can find one. What about maybe copper solid or silver? What about gold? Where's gold on this list? Oh, it's way up here. Will these metals react with all strong acids and dissolve and corrode away or not? They won't, will they? And why is that? Because don't these metals want to be reduced more than our hydrogen down here? So in fact, that's what's going to happen. Silver, gold, copper, they won't react with all strong acids because they prefer to be reduced more. So if the metal is above the SHE reaction in the table, that metal will not react with strong acids. However, if the metal is below, it will react with H plus. All right, so zinc will certainly react with strong acids. Looks like manganese is going to react with strong acids. Elemental aluminum will also react. God forsake, gosh, magnesium and sodium, elemental, that stuff is very reactive, right? But cadmium, nickel, all these, tin, all of these below the hydrogen will react with strong acids. And that's how we can tell, just by their relative placement on the table, okay? So you don't even have to calculate the E0, you can just tell based on where they're placed in the table oftentimes. Now I also mentioned on this slide a very specific point about HNO3. This is nitric acid. It's one of our strong acids. Now this sometimes causes some confusion. Say metals dissolving in acid. And you may seen experiments where you can actually take a copper penny or a piece of copper and dissolve it in nitric acid. So you say, well, why does that work? Or I just said that copper and gold and things like that these more stable metals, they don't react with H+, but they do react with HNO3. The key idea to understand is this reaction. HNO3, nitric acid, is a strongly oxidizing acid. In fact, chemists often use concentrated solution of HNO3 to dissolve up metals. And the reason why it works is not so much the H+ component, which is freely donated, but the nitrate ion component. In acidic conditions, such as would be produced in a concentrated solution of nitric acid, we'd have plenty of H+ around. But in acidic conditions, that nitrate anion can react to be reduced to NO gas. It's a different reaction. It's not the reaction of H+ getting reduced to H2 anymore, is it? It's a completely different chemical reaction. And the thing is, if we look up this reaction on our table, let's see where we find it. I'm going to go back to that table again. See where we can find that one. I'm going to zoom in a little bit. Oh, I have it highlighted already for us. Okay. I think we used that in a previous problem. Isn't that reaction all the way up at 0.96 volts? That one's pretty high on our table of reduction potentials. So we at least have a chance at employing that one to oxidize metals. Now, you notice it's still below gold, right? In some cases, we can actually use that reaction to actually dissolve up gold. But we have to actually help out the system a little bit more. There's this mixture of acids. It's a mixture of nitric acid and HCl. It's called aqua regia. I have that named right there, aqua regia. It turns out this kind of interesting chemistry, and it's a little bit beyond the scope of, I guess, what we're talking about here. But this aqua regia is this mixture of nitric and hydrochloric acids. And it just so happens that the chloride ion that's produced from HCl when it dissociates can also form a complex ion with many of these precious metals in solution, and that encourages their dissolution and solubilization and oxidation. So as a result, this aqua regia is sort of famous, actually, because this mixture of nitric acid and HCl can actually dissolve up and oxidize these precious metals. It's one of the few solvents that are able to do that, okay? So indeed, we can use our table of reduction potentials, standard reduction potentials, to predict whether a metal will dissolve and react with an acid. All right, there's two more concepts that I want to get at here in this video, and then we're going to take a break and we'll move to that second video for the lecture where we're talking about non-standard conditions. But before we do that, I want to tie in two more concepts. Now this semester we have spent a lot of time talking about equilibrium and equilibrium constants K, haven't we? Last chapter, we spent a significant amount of time talking about the change in Gibbs free energy for a reaction. And now we're following up by talking about E0 cell, the standard cell potentials for any redox reaction that we want to talk about. We just learned how to compute that. Are there equations which link the three of these together for us? Wouldn't that be a fun thing if there is an equation that could link all three of these concepts together? It turns out that there are such equations, and that equation is basically listed right here in the middle of this slide, okay? Let's take a look at these, understand what's going on. It just so happens that the change in the Gibbs free energy for a reaction, a redox reaction, can be set as being equal to negative N times F times E cell. Let's talk about what all these variables are. Now, earlier in the previous lecture, we learned what F was. That was our Faraday's constant, wasn't it? And I warned you at that time that you would see that number in some equations. Remember, it was 96,485, okay, coulombs per mole. That's what that number is, all right? So that's the F. There are some other values that we have to multiply by that, though. Well, we've got our E cell. What about that? Well, we just learned how to compute that. That's what? Our standard cell potential for the reaction as it is written. In other words, you have to consider what's being oxidized, what's being reduced, and compute that standard cell potential correctly. But if you can do that, you can put a number there. All right, we just learned how to do that, so that's no big surprise. But what about this third number, n? And notice that it's negative NFE, okay? What about n? What is that? Well, n is the number of electrons involved, well, number of electrons which are involved in the balanced chemical reaction. How many electrons are being transferred to complete the reaction as it's written? And I'll tell you right now from experience, students sometimes struggle finding this number. So I'm going to explain how to do it in a sample problem in a few minutes. But spend some time on that. Make sure you understand that. It sounds like it's an easy concept, how many electrons are transferred in the balanced chemical reaction, but you really have to pay some attention to that, okay? I'll show an example how that works, and it's best done through an example, so I'm going to wait to clarify that further until we do an example problem, but we're going to do that in a second, okay? But that's what n is. It's the number of electrons transferred in the reaction. So we can relate delta G for our reaction, change in Gibbs free energy. And that predicts spontaneity, remember? If delta G is negative, the reaction's spontaneous. But we can relate that to cell potential, standard cell potential, as negative NFE. And notice that this negative sign's in that equation. What does E0 cell have to be to make the reaction spontaneous? The E0 cell had to be positive. But Gibbs free energy has to be negative. Well, guess what? That negative sign takes care of it for us. The change in sign doesn't it? Okay, but so don't forget it has to be negative. All right. There is also an equation that allows us to compute or interrelate delta G with the equilibrium constant. And we actually talked about this one last chapter. Remember that delta G is equal to negative RT times the natural log of K, where K is the equilibrium constant. R is that gas constant, 8.3145, and then T is the Kelvin temperature. We actually talked about that in that previous chapter leading up to our third exam. Well, now we can relate the equilibrium constant for our reaction with standard cell potential, can't we? Because all these terms are equal to one another. All right, so we've got these equations. They're pretty flexible. We can go between K, our Gibbs free energy change, our cell potential, all these things that we've learned about all semester. How can we put this into use? Well, now it's time to work this sample problem down below. Let's practice this a little bit. So we want to use the tabulated electrode potentials to calculate a delta G for the reaction that's given, and it looks like it's balanced already for us, okay? We want to know, is this reaction spontaneous? Well, if we compute delta G, we better be able to tell whether it's spontaneous or not. Remember, if delta G is negative, a negative number, that tells us, yes, it's spontaneous, as written, okay? So can we compute delta G, and can we figure out, is this spontaneous or not? So all these things are sort of intertwined at this point because of that equation that we just talked about. All right, so we're told to use the tabulated electrode potentials for this redox process. So we go about our process that we've already learned about. Let's compute our E0 cell, our standard cell potential. Got to compute that first. So how do we do that? Well, again, we break this chemistry down into two half reactions, one for the oxidation, one for the reduction. That's what our first step in our solution always is. So we look at the oxidation. What's been oxidized here? Well, I know if the bromine goes to a 0 oxidation state, it starts off at a -1. So it looks like that's our oxidation. So 2Br, making Br2. And because we're using 2 copies, that's a 2 electron process. Now, we then need to decide on our reduction reaction. So what's that? Well, it looks like iodine here is in its elemental state, it's oxidation state of 0, but over here it's -1, isn't it? So iodine is reduced to I-, the iodide form. So we write an equation for that half reaction. 2 copies of molecular iodine, I2, solid, getting reduced to 2 copies of I-. That is also a 2 electron process. So the beauty of this is when we combine these half reactions to generate our overall reaction, 2 electrons are produced, 2 electrons are consumed. It balances. So what I'm getting at here is N for this reaction. Remember I said that was sometimes difficult to find? It's 2. N is the number of electrons that are involved in the overall chemical process. How many electrons are transferred as decided upon by the overall reaction. And here that's 2, okay? Sometimes that's the hardest part of these problems for people, but we're going to get back to that. We're not going to use that right now, though. But what we are going to do first is we're going to find the standard cell potential. Now that we know what's the oxidation and what's the reduction, we can look up the values from the table. So these are from the table, right? FR from table. Numbers that are in the entries for the very specific reactions, okay? And all we do is we apply our equation for each cell. The cathode minus the anode. Now what's the cathode? That's the reduction. So we take the positive 0.54 volts and we plug that in and we subtract the value for the anode or the oxidation. So in this case, to find the standard cell potential, we would do what? 0.54 minus 1.09. Notice that both of them come along with the signs from the table. They're both positive. And then when we do that, we get the negative 0.55. So this number is our E0, isn't it? For this reaction. It's our E0 cell. So just for labeling purposes, I guess I should say it's E0 cell. So that's the standard cell potential, we'd call that, for this redox couple. Now we're not asked that in the problem. We want to find the delta G, so how can we do that? Well, all we need to do is use this equation, okay? So we kind of plug and chug at this point. We don't know what delta G is, but we're going to find it. We know that delta G is equal to N times F times E, 0 cell. So we plug in the values. Now I said that since this balanced chemical equation involved 2 electrons, N is equal to 2. F is our Faraday's constant, 96,485. It's just that constant. E0 cell we found to be negative 0.55 volts. Notice the different units down here now. We usually throw around volts as our unit for E0 cell, but remember, I think it was last lecture, we talked about what alternate units for volts are that are equivalent to volts. Remember, it's the energy required to basically move charges, a coulomb of charge somewhere, through a circuit. So it has joules per coulomb units. And now that shows up here, just to show us that the coulomb units will cancel, and the moles of electrons will cancel. And in doing so, we get a delta G with energy units, which is what we should have in joules. So that's all we need to do. We plug and we chug. I'm not sure if this is worked out on the next slide. It's really not, okay? Oh, it's on here in the bottom, okay. We plug and we chug and we find an answer for delta G. Positive 1.1 times 10 to the 5th. So is this reaction as written spontaneous? No, it's not. And how do we know that? Well, delta G is a positive number, isn't it? If delta G is a positive number, the reaction's not spontaneous. We also had a hint earlier, didn't we? When we computed our E0 cell, wasn't the E0 cell a negative number? When E0 cell is negative, that tells you the process is non-spontaneous. So both of these are internally consistent. This is not a spontaneous process at all, is it? So this reaction, as it's written, is not spontaneous. And what that means is that if you mix solid iodine with bromide ion, this reaction does not happen. You don't get I- and Br2. In fact, the reaction would occur if it was written in reverse. What I mean by that is if I wanted to make a reaction occur between these reactants, what I would need to do is mix these together. In other words, the reverse reaction would be spontaneous, but the one that's written is not. Okay? And that's what we mean by predicting whether the reaction is spontaneous or not. All right, moving on then to I think what's the last slide here of this particular discussion. On the previous slide, we defined this equation that relates E0 cell, equilibrium constants K, and delta G. I figured that maybe we could look at a sample problem now to actually understand how to relate some different terms here, okay? So to help us with that, let's look at the sample problem. We're to use the tabulated electrode potentials to calculate K for the oxidation of copper by H+. Now, seems like earlier in this class we decided that copper was above H+ on our reduction potential table. So I don't know that this reaction is really going to take off. I mean, if we look at it, what are we doing? We're reducing the hydrogen to H2, and we're dissolving the copper. This is the topic of, that taking those metals and dissolving them in concentrated acid, basically. And we said copper probably doesn't react. So I'm guessing right off the bat here that my equilibrium constant for this reaction is going to be vanishingly small, because that reaction does not really occur. It doesn't pick up steam, and we don't get the dissolution of copper metal. It's one of our more inert metals. But let's prove that quantitatively. To help us do that, we are going to use our tabulated electrode potentials to compute the equilibrium constant. So where do we start? Well, we start in the usual place. We look at what's oxidized and what's being reduced. So I'm looking at the copper, and it's being oxidized. It's being corroded, isn't it? That's our oxidation. That is by default our anode. It's our anodic reaction. So we write that. Copper solid making copper 2+. It's a 2-electron process, right? To go from here to here. 2 electrons are involved. That's our oxidation. Now I look at the value from the table for that reaction involving these two, the copper and the copper 2+, and I get a positive 0.34 volts if I look at the table. Likewise, I write the reaction involving the hydrogen, and this is my reduction, right? We're reducing H+ to get H2 gas. It's also a 2-electron process. Now I know I don't even need to look at the table for that one, because that's the reduction of hydrogen. That's my SHE reaction, isn't it? And by default, I get a 0-volt potential for that. So these are my standard reduction potentials for each half reaction. That's what they're called, standard reduction potentials, right? So I look them up on the table, and then I make sense of all this. Well, okay, I use my usual formula. E cell is my cathodic reaction minus my anode reaction. What's my cathodic reaction? It's the reduction. So what do? 0 volts for my SHE, and I subtract the value for my copper. That's my anodic half reaction, or my oxidation. That's 0.34, and when I do that, I get negative 0.34 as my E0 cell, don't I? Negative 0.34, right? And of course that's shown here in the answer. I just wanted to kind of work that through with you to make sure it was clear where that number came from. But indeed, that's shown right here. Negative 0.34 for my E0 cell. That's what it's equal to. Now, can I use the equation that we just learned about to interrelate that E0 cell with an equilibrium constant K? I bet I can. All I need to do is use the equation, okay? And that's what I'm going to do. So I look at my equation that interrelates my two variables, okay? Which is essentially this one right here. Oops. Basically any of these, okay? And then I plug in my numbers. And my one equation of interest here is that the E0 cell is equal to 0.0592 divided by n times the log of K, which is my equilibrium constant, isn't it? So I plug in what I know and try to solve for that, basically, okay? Now, do I know my E0 cell? I do. It was negative 0.34. So I basically just take that and then plug that into the equation. It looks like they did a little bit of algebra for us here to rearrange, but we're basically plugging that directly in, okay? And I have this 0.0592 over n. And it looks like they did a little bit of algebra when they solved for log of k. So they had to divide both sides by this term, and that's kind of why it appears like this here. But n still is nothing more than the number of electrons which are transferred in the balanced redox reaction, so that's just 2, isn't it? So I do the math, and I find that log of k is negative 11.48. I take the anti-log and find that K, my equilibrium constant, is 3.3 times 10 to the minus 12th. Indeed, that number is very, very, very small. And because of that, I can predict that indeed this reaction will not proceed to the right to an appreciable extent at all. Tiny, tiny, tiny number. And strong acids such as H+, do not oxidize copper or metals which appear above them on that table of standard reduction potentials. All right, so hopefully that kind of makes a little bit of sense to you, okay? Now, one more thing I just kind of want to clear up, and unfortunately, when I put this slide together, I did not pay close enough attention to this. But I really don't want to confuse anyone, so I'm going to backtrack just a little bit more in this particular problem. And when I put the answer in here, I wasn't very careful. So I want to address that at this point. What I want to look at is going from this equation down to this one, okay? Because in kind of one swoop, I think that the slide does that, and unfortunately it does not do a very good job of explaining it. And when I just went through it, I kind of glossed over this just to get at the answer, but I think we should talk about it, okay? So how does this happen, right? So, basically down here, it looks like they've already solved for my E0 cell, which is one of the terms in the equation up here at the top, but it's not the only term, is it, right? So it looks like we need to do a little bit of work to derive that equation. So that E0 cell, if I was going to isolate that by itself, okay, using these two equations setting equal to one another, how could I do that? Well, it looks like to me what I would need to do is do negative RT over negative NF. Okay, so negative RT over negative NF, but then I'd also need to multiply by natural log of K, because that kind of comes along for the ride there, doesn't it? Everybody see that? All right, now the negative signs would basically cancel each other out, and you'd have RT over NF. Now again, what are all these numbers? I guess that could be potentially a mystery to you also. Let's talk about what the numbers are. You've actually seen all of them before. This F is our Faraday's constant, which is the 96,485. This N is the number of electrons transferred in the reaction. So here that's just a 2, okay? And actually that shows up in our equation as well, so they don't really substitute in for that, but eventually they'll substitute in a 2, but not in this initial derivation, okay? But the F is the Faraday's constant. It never changes, right? Now T, up top, is our Kelvin temperature. Now, since we're operating this cell at standard conditions, that's 298, isn't it? It's got to be 298, because it's standard conditions. And the other term that was up there was what? The R. It's that 8.3145 business that we learned about, and I'm running out of space, was 8.3145, okay? So basically what I'm saying is if you plug those numbers in, and you plug this 96,485 in for this F, and one more thing. They converted from a natural log to a base 10 log, which involves a factor of 2.303 to do the conversion. It's just a constant 2.303. But basically, if you plug those numbers in, and you account for this conversion from natural log to base 10 log of this factor of 2.303, you basically end up with the equation that is shown right here. So they converted from natural log to LOG in the process, okay? So this is actually another form of essentially this equation that relates these two variables. It's just with a base 10 log instead of the ln. And then for any constant that remains a constant for any cell at standard conditions, they basically plugged in the appropriate value. So they put the 298 in, the 8.3145, and the Faraday's constant. And they just simplified the equation to this form. And that's all they're doing here, okay? So after that, it's just plug and chug. All right, but nonetheless, we get the same result. We would have got the same result if we just would have used this relationship as well and plugged in the appropriate values. So no real big deal. But either way, either equation, we found K for this reaction is a very small number. And because of that, we would not predict this spontaneity of this reaction. It does not proceed to the right very much at all. All right, so that's this video. Now in the next video, we're going to talk about non-standard conditions, okay? All we've done to this point have this zeros, don't they? These are standard conditions, but not all redox reactions always occur under standard conditions. In fact, it's fun to make them non-standard. And that's the basis for potentiometry, where you measure the potential at different concentrations of reactions. We can actually measure the potential and relate it to the concentration of reactants if we're able to work problems at non-standard conditions, and that's coming up next, all right? So stay tuned.